Okay, so we have our unit test on Thursday, so this is kind of like a pretty good summary of what we're going to see on the test, okay? So this is hopefully a good gauge for you guys to recognize what we need to work on, what we need to practice a little bit more, okay? So hopefully this will be helpful for you. Okay, so first thing, we were talking about the difference between a scalar and a vector quantity. So remember, scalar only describes the magnitude, okay, and not where it's going, where vector will describe the magnitude and direction. Okay, so remember, scalars are like simple, right? Simple scalars only have the amount, and vectors have both the magnitude and the direction. Okay, so distance or displacement, what is scalar, what is vector between distance and displacement? Distance is scalar, perfect, and displacement is vector, good. And what about speed versus velocity? Speed is scalar, good, and velocity is a vector. Okay, good. Speed is scalar, s, velocity vector. Okay, should be easy for us to remember. Okay, so make sure you know the difference between those two. And probably the most important one is the distance versus displacement. Okay, just like that very first question that you guys saw, you need to be able to recognize the difference between distance and displacement. Okay, so our first example, while I teach, I walk back and forth to the front of the classroom like I'm doing right now. If I start at my desk, okay, so if I'm right here, and then I walk 5 meters north, I pause and I talk to Brody and Tanner, right? And then I walk 5 meters south again to have a sip of coffee. And then I walk 2 meters north to write some notes on the board, okay? All in a time period of 20 seconds, okay? So how far did I walk in total? 12 meters, right? Because I went 5 meters to this point, I walked 5 meters back to the desk, and then I walked 2 meters up to the smartboard. So my total distance is equal to 12 meters. And no direction on distance because it is a scalar quantity. Okay? So now my average speed. So remember, average speed is v is equal to distance over time. No vector caps. Okay, because these are scalar quantities. I walked 12 meters in a total of 20 seconds. So we punch that into our calculator. We will get a value of 0.6 meters per second is what you get. Okay, but let's not forget about sig digs. We have 2 and 2 and 2 and 2 all given in the question. So our answer should also have 2. Okay, so we're just going to put a little another 0 beside it, and our units are meters divided by seconds, so meters per second. That is my average speed. Okay, that is related to distance, not displacement. Which brings us to the next question. What is my displacement from the origin? So if the desk was my origin, and now I am 2 meters north of that, right? I am 2 meters north is my displacement, okay? Even though I went forward and back and then forward again, my displacement is only 2 meters, okay? So average velocity, so this is where we have our vector cap, so velocity is equal to displacement over time. My displacement is 2 meters north, another square bracket, divided by that time period of 20 seconds. Okay, we put that into our calculator, you will get 0.1. And again, we have 2 sig digs given in the question, so we will give our answer in 2 sig digs. And because this is velocity, what must I include here? Direction as well, okay? Good. So my average velocity is 0.1 meters per second north. Okay, note that this is different than my average speed, right? So speed and velocity, similar, but different. Okay, displacement time graphs. So I just wanted you guys to write this note in that little area there. So if you are given a displacement time graph, or if you're given any graph in general, okay, first thing we need to do is check what type of graph we're looking at, right? So this one is a displacement time graph. If you have a displacement time graph, we can calculate the average velocity of a displacement time graph by calculating the slope, okay? By calculating the slope, we can find the average velocity of a graph, okay? What is the formula for slope? Is equal to the rise over the run. Good. Now, in this case, because it is a displacement time graph, my rise is going to be my displacement, or my change in displacement, and my run is going to be my change in time. Okay, so if I wanted to calculate the average velocity here are my 2 points of interest. And when you're calculating the change on a graph, okay, it's your second point minus your first point. So D2 minus D1 over T2 minus T1. So again, these are my points of interest here. Up here I have 4 and 40. Okay? When you do have a graph, feel free to write the coordinates of your pair or your point on there. Okay? It might just help you kind of make that connection between the final and initial. Okay? 0 and 0 is my initial. So my second distance, or my second displacement, is 40. My first displacement is 0. So I'll have 40 meters minus 0 meters divided by my second time divided by my first time. So 4 seconds minus 0 seconds. Now I will get my slope, which in this case, because it's a displacement time graph, will be my, if I calculate the slope of a displacement time graph, I will find my average velocity, right? So here, my velocity is 40 divided by 4, which is 10 meters per second. Okay, so that is my average velocity here. Okay, so make sure you guys are able to calculate slope and know that when we have a displacement time graph, we can find the average velocity. Okay? Okay, if it is a velocity time graph, we can calculate the average acceleration by calculating the slope of a velocity time graph. Okay? So make sure you know that. Okay? And secondly, and I know some of you guys forgot how to do this, okay? To find the total displacement given a graph, you just find the area underneath the graph, right? So to find the total displacement, you're going to divide this into shapes. So 1, 2, and 3. Okay? What were you guys asked to do? You needed to find the acceleration between 1 and 4 seconds. Right? So we care about this point right here. Okay? So my ordered pair up here is 4 seconds and 8 meters per second. And down here we have 0 and 0. So to find the acceleration between 0 and 4 seconds is equal to change in velocity, which is my second velocity minus my first velocity divided by my second time minus my first time. So my final velocity, or my second velocity here is 8 meters per second minus my initial, which is 0 meters per second, divided by my second time, which is 4 seconds, minus my first time, which is 0 seconds. Okay? So, our units on here for acceleration, it's always meters per second, right? And another way of saying that is meters per second squared. Okay? And if we do not remember the units on that, we can just look at our formula here, right? Meters per second per second. So those will be our units, meters per second squared. And our value is 8 divided by 4, which is 2 meters per second squared. Okay, that is the acceleration between 0 and 4 seconds. Okay, the second thing you guys were asked to do was to find the total displacement. Okay, so for that we just need to find the area underneath the graph. Okay, so we've already broken this up into shapes, so I'm just going to jump up here. So shape 1, we have a length of 4 seconds and a height of 8 meters per second. So 4 seconds times 8 meters per second divided by 2, because it's a triangle. Seconds will cancel. 4 times 8 is 32, divided by 2 is 16 meters for shape 1. For shape 2, it's just a length times height, so we have 5, 6, 7 is 3 seconds times the height, which is 8 meters per second. Seconds cancel again, then we get 24 meters for shape 2. And for shape 3, it's a triangle, so our base is 1, 2, 3 seconds again, times the height, which is 8 meters per second, and it's a triangle, so we'll divide it by 2. Seconds cancel. 3 times 8 is 24, divided by 2 is 12 meters. So last thing we need to do is add those up. So 16 plus 24 is 40, plus 12 is 52. So the total displacement is equal to 52 meters. Okay, so I saw a few of you guys trying to calculate the displacement using a formula. Okay, and you know that you know your change in velocity, right? It's just going to be a little bit more difficult to do it that way. Okay, so if you're asked to find total displacement on a graphing question, just find the area underneath the graph. Okay, probably the easiest. Okay, we just did this. Good. Okay, so example 2 is velocity. Okay, so remember that velocity is a change in displacement over a change in time. Okay, so this object moves 37 meters north. So that is our displacement. And we know our time is 20 seconds. So we know our displacement, we know our time. We can just punch that into our calculator. So 37 meters north divided by 20 seconds is equal to 1.9 meters per second north. Okay, that one was pretty straightforward, just plug and chug, right? So if you were finding yourself having challenges with this one, please let me know. Okay, we need to get that sorted out before Thursday. Okay, this next one. So calculate the acceleration of a car. This starts from rest and reaches a speed of 120 kilometers per hour in 20 seconds. Okay. I think the challenging part, or the curveball, associated with this question is putting our units in meters per second, right? Because we're given our speed in kilometers per hour, right? So if you were to just go in and do velocity over time without changing the units, you would get kilometers per hour per second, okay? We don't really like those units for acceleration. Okay, so we need to change this kilometers per hour to meters per second. And the way that we do that is dividing by 3.6. Okay, so if you divide by 3.6, you get 33.3 repeating meters per second. Okay, so now we have our velocity in the right units, meters per second. And we also know our time is 20 seconds. We can go ahead and find our acceleration using this formula here. So acceleration is equal to change in velocity. It was starting from rest, right? So Vf minus Vi over t. Our final velocity is 33.3 meters per second minus 0 meters per second divided by our time, which is 20 seconds. So we punch those into our calculator, and you get, this is like 1.666666. That's what you guys get? Yeah? Okay. So again, don't forget about significant digits here. So we have 3 and 3 given in the question. Okay, so we need our answer to also have 3. So don't forget to round, because our answer is 1.67 meters per second squared. Okay? So make sure that we check out our units when we are reading the question, okay? Those are important. Okay, example 4. So a car is slowing down as it approaches a red light. So it's having negative acceleration, right? It's slowing down. So we know the rate at which it is accelerating. So acceleration is equal to negative 4.19 meters per second squared east. We know the initial velocity is 30 meters per second. Vf. The car is coming to a stop. What is my final velocity? 0. Okay? 0 is my final velocity. And I'm looking for the time. Okay, so remember, any time that you see a delta, it can be expanded to Vf, or final minus initial. And in this case, we're asked, what is our time period, right? So we can just leave delta t as delta t. Okay, so we are solving for delta t. So we have our formula, A is equal to Vf minus Vi over t. How am I going to get my time all by itself?
You multiply it by time.
Perfect. And are we going to do that to one side?
No.
No, we will do that to both sides. Yes, you're absolutely correct. You could, but you get the wrong answer. Okay? And now, how am I going to get time all by itself? Divide by acceleration. Good. So anything divided by itself is 1, so that will just go away. So time is equal to Vf minus Vi over acceleration. Okay, now that we know our variables, we can just plug those in. So we get what is our Vf? We are stopping, so it will be 0 meters per second minus 30 meters per second divided by our acceleration, which is negative 4.19 meters per second squared. Okay, when you are dividing this, your units Meters and seconds will cancel here because you have seconds in your denominator. Of the denominator, it becomes your numerator. If all that didn't even make sense, just, you know that time is measured in seconds. So time is equal to 7.16 seconds. Okay, don't forget to round and sig digs. How are we doing so far? Good? Yeah? Okay, moving on to work and forces and energy. So remember, for there to be work, you need to have movement, and that movement must be in the same direction of the force, right? So if you lift up a bag and then start walking with it, because the force you're applying to the bag is not in the same direction as your motion, you're not doing work on the backpack. Okay, you are still doing work yourself, but you're not doing work on the backpack. Okay? Same with the groceries. As you lift it up, you're doing work, but then as you start walking to the left, right, you're no longer doing work on the bag of groceries, but you're doing work on yourself, moving it. Okay? Remember that a force is just like a push or a pull on an object. Force is measured in newtons. Okay, if you're wondering what a fundamental unit of a newton is, it's a kilogram meter per second squared. If you're like Mr. Jones, I don't care. That's okay too. What you guys need to know for Science 10 physics, force is equal to mass times acceleration. Okay, so if I wanted to calculate my force here on Earth, I would multiply my mass by the acceleration due to gravity on Earth. Right? That's where we're at. Okay? And this brings us to work. So work is done when energy leads to a change in the position of an object. Like you have to invest energy to move things, right? Like this marker is not just going to move by itself. I need to put energy there. We need to remember that work, this will be on your formula sheet, so you don't need to remember it, but know that work is change in energy. These are both measured in joules. And work is equal to force times distance. Okay, so example 5. So I have a bow and arrow. So to pull that drawstring back, I apply a force of 10 newtons. And I pull that drawstring back 0.25 meters. Okay, so how much work have I done? Well, work is equal to force times distance. My force is 10 newtons times my distance, 0.25 meters. So work is equal to 2.5 joules. Okay, are you doing all right, gentlemen? Okay, so I have done 2.5 joules worth of work in pulling back that drawstring. Okay. So before I release it, so I have it all ready to go, and I have not released it. What type of energy do I have in the bow? Potential, right? Good. I have potential energy. Okay. And how much do I have? I have the amount of energy related to how much work I put in. So that is going to be equal to 2.5 joules. Okay, so I loaded up the bow and arrow. It now has 2.5 joules of potential energy, and it's ready to go. Right? It's just kind of hanging on. The bow is loaded. Okay. So just summarize what we just talked about. I put in work to give the system potential energy. And if I release the bow, the potential energy will be converted to kinetic energy, right? Just like with this thing, if I lift it up, it has potential energy. As I let it go, that potential energy is being converted to kinetic energy, right? So same thing here with the bow. If we know that the arrow weighs 100 grams and it has, when it's released, that potential energy is being converted to kinetic energy, right? So the instant it is released, it has 2.5 joules of kinetic energy. Okay, the mass is 100 grams. Do we like grams as a unit?
No.
No, we do not like grams. Okay, we like grandmas, but we do not like grams. Okay, so we will fix this into kilograms. So 100 grams is equal to 0.1 kilograms. And to do that, you can just divide by 1,000. Okay, and we're asked what is the speed of the arrow. So what is our V? Okay, so we know kinetic energy, we know our mass. We just need to solve for velocity. So we know our formula for kinetic energy is 1/2 mv squared. What is the first thing we will do when we're trying to rearrange this formula? Yeah, we're going to multiply by 2 to get rid of that fraction. Okay, perfect. So multiply each side by 2. Those will go away. Now I have 2 EK is equal to mv squared. We are solving for V, so we will divide both sides by mass. Masses cancel. And lastly, I'll take the square root of both sides. And now I am left with velocity or speed is equal to 2 times the kinetic energy divided by the mass. So 2 times 2.5 joules. And just be careful with your calculator here. I hate for you to get this far and not get the right answer. Divided by 0.1 kilograms. And again, sig digs and units are important, of course. And we get a velocity of 7.07 meters per second. Or a speed. Yeah. Yeah. All right. So make sure you guys are able to make that connection between work and energy. Okay. If you put in work, you get energy, and if if like potential is being converted to kinetic, make sure you're able to make those connections there. Okay, we have lots of different forms of energy. For the sake of Science 10, we really only focus on kinetic and potential energy. Okay, so make sure you're able to solve questions involving those. If you're interested in electromagnetic energy or electrical energy, or nuclear energy, or mechanical energy, that is Physics 20 and Physics 30. Split. Okay, so the two main types of energy we are going to discuss and solve problems related to is kinetic energy and gravitational potential energy. Okay, so kinetic energy is the energy associated with motion. So if you're moving, you have kinetic energy. If you are not moving, you have 0 kinetic energy. Yeah, so anytime that you have a question that says something is moving, okay, really good indicator, you're using the kinetic energy formula, okay? So don't try to use potential energy when you have kinetic energy, okay? Because gravitational potential energy is the energy of an object based on its position above Earth, okay? Not the same. So kinetic energy, EK is 1 over 2 mv squared, and EP is equal to mgh. Okay? Different formulas, so know when to use each one. So potential energy, this is stored energy that has the ability to do work. And we have chemical potential, elastic potential, and gravitational. We are really only going to focus on gravitational. Time for a joke. The physics teacher told me I had potential, and then he threw me off the roof. Huh. I wouldn't throw you guys off the roof. I'll let you guys do that. Huh? Ha. I'll get the sign out. Okay. So just to reiterate what we've been talking about, so potential energy is the stored energy of an object before it is dropped. The force of gravity pulls things towards the Earth, and that value is 9.81 meters per second squared. You have that on your formula sheet. And remember, their mass and weight are different, right? Mass will be the same no matter where you are in the universe, and your weight will be different depending on which planet you're on, unless you cut your arm off. Okay, so we've already talked about that. Okay, so skydivers jump from up to altitudes up to 3 kilometers above the surface of the Earth. What is the potential energy of a skydiver that weighs 65 kilograms? Okay, so we know it's asking us what is our potential energy. So a good indicator to use our potential energy formula. We know the mass of the skydiver is 65 kilograms. The height of the skydiver is 3 kilometers. Do we like kilometers? No, we like meters, right? If you are not sure in which units we like, okay, look at these boards, look at all of these formulas up here. Not to be like, don't worry about them, but these are physics friendly units, okay? So kilograms, meters, and seconds, okay? Kilograms, meters, and seconds. So 3 kilometers is 3,000 meters. To do that, you can just multiply by 1,000, okay? Because there are 1,000 meters in 1 kilometer. Okay, and G is not given. Is that okay?
Yeah.
We know G, right? We know G. G is 9.81 meter per second squared. So we know M, G, and H, so now we can just plug this into our formula. So 65 kilograms times 9.81 meters per second squared times our height, which is 3,000 meters. So if we punch that into a calculator, we get a big number, 1912950 joules. Am I going to leave my answer like this? No. We want to put it into the right amount of sig digs, right? Because right now this has 2, 4, 6, 7 significant digits, and we want it to only have 2. Okay, so here is a scientific notation refresher, okay? So when you get a number like this, if you do not see the decimal, just assume that it is at the end of the number, okay? So now we want to change this big digit so that it only has 2. Okay, it only has 2. And we need to just be concerned with the number to the right of it. It is less than 5, so we will not round it, right? We're just gonna leave the 1 alone. Okay, so now let's put this 2, 4, 6, 7 digit number or answer into 2 digits. So we're gonna move it 1, 2, 3, 4, 5, 6 spots. Okay, so now our final answer, potential energy is equal to 1.9 times 10 to the 6 joules. All right. Okay. So, a textbook is on a shelf. So mass of the textbook is 1 kilogram. It has potential energy, EP is equal to 5.7 joules. What is given but not given? What's not given in the question but we always know? G, gravity, right? Okay, we know G is 9.81 meters per second squared. So we are looking for our height. So potential energy is equal to mass times gravity times height. We need to get H by itself. Divide both sides by mg. H, height is equal to potential energy divided by mass times gravity. And again, be careful with our calculators here, okay? Because you could potentially get the wrong answer. So 5.7 joules divided by, and if I were you guys, I would put brackets around the bottom here. 1 kilogram times 9.81 meter per second squared. And then you'll get a height of 0.58 meters. Okay. Just a couple more examples to get through. Okay, so kinetic energy, energy associated with motion. We've talked about this today. Here's our formula, and here's an example. Okay, so when skydivers free fall, their max speed due to air resistance, so we call that terminal velocity, is 50 meters per second. What is the kinetic energy? So EK. What is the kinetic energy of a 60 kilogram skydiver falling at terminal velocity? Okay, so we know velocity, we know mass. We can just plug this into our formula. EK is 1 over 2 mv squared. 1 over 2, 60 kilograms times our velocity, 50 meters per second. Now, just be careful with this one, okay? Because some of you guys did not square this, okay? And it's not the units that are being squared, it's the number, okay? It's 50 squared, not meters per second squared, it's 50 squared, okay? So just be careful when you put those into your calculator. And don't forget to square it as well. And you get a kinetic energy of 7.5 times 10 to the 4 meters per second. Joules. Joules for energy. Okay. Did anybody get to example 9? Just a couple? Okay. I will just hang off going over that until tomorrow, okay? Because I wanted to talk about efficiency and energy conversion first. Okay? Okay. So you guys did your projects last 2 days of last week. Okay, I have not marked them or even looked at them, to be honest. But we just want to, I got to go over this before we go any further. Okay, so we have talked about energy conversions and efficiency already. Okay, one thing we need to talk about is limitations and drawbacks of some of these energy conversion methods. Okay, so we know in a hydroelectric dam we have potential energy that is converted to kinetic energy, which rotates a turbine, which then creates electrical energy. Okay? This is all good for us. We like that. And water flows, so that's pretty good for us. But does anybody know what is a limitation of hydroelectric dams? Has anybody been to Hoover Dam in the States? Really big. Big dam. Does anybody know how they build dams? No? So is what they do, we'll say they have like a river that's running through there, and if they want to make a dam, say right here, is what they will do, they'll like blow up the river to reroute it. So the river instead will go like this and then join up again. And while that river has been rerouted, so this river bed will end up drying out, right? Because there's no water going through it. And then that's when they're gonna go and like construct their dam. So they actually have to like reroute the river to build the dam. I didn't know that. I thought that was like pretty interesting. So I'm like, wait a minute. If they have all of this flowing water going through this dam, like how do you build it, right? But they just tell the river to move over. Okay, so we just talked about one limitation or one drawback of building a hydroelectric dam. What was it? Yeah, it's related to the river, right? So to build it, they gotta like blow up the river to move it, right? So they have to reroute the river. And then after they build up this big reservoir, what happens behind the dam? Where does all that water go? Builds up, right? So what is going to happen to all of this land? And where's the green marker? Perfect. So all of this land, if this was like before, if the river was just like glowing through it all peacefully, right? You're probably gonna have, you know, like some shrubs, some trees around the side, maybe some deers, you know, maybe some humans, right? And then after they build that up and they block all that water, it essentially floods the entire area, right? So it turns what could be, you know, land into floodplain, essentially, right? So this changes the actual like landscape of the area surrounding a dam. So that is one challenge with that. And it also will affect the migratory patterns of fish, because some fish are, you know, not able to make it through a dam, right? Some fish need to go upstream to spawn. Okay, so make sure you know those two. Okay, make a note of that. Okay, it affects the landscape, and it also affects aquatic organisms. Okay, we will leave that here and we will finish that up tomorrow. I just have like 2 quick things to go over tomorrow, and then the rest of your day is for you guys to review.